Welcome, CalcAB. This is section 2.6, related rates. The essential question is, explain the difference between dV/dt, dH/dt, and dR/dt. Go. So, we've used derivatives to find instantaneous rate of change, and we found dy/dx implicitly using the chain rule. So, another property of the chain rule is we can use this to find the rate of change of two or more variables with respect to time. So this is the catch right here. When I say derivative with respect to time, we're going to use this notation d/dt, t being time. So we'll say dy dt or dx dt, or derivative of volume with respect to time. So it's always going to have d over d of t on the bottom here. Let's actually talk about why we do this. So what if we have a shape here like a conical tank right here, and I want to find the rate of change as it's draining water from the bottom. So we know the volume of a cone right here is going to be pi over 3 r squared h. But how are we going to do this is we're going to differentiate with respect to time to compare the rates of change of volume, the radius, and the height. So here's the start right here. d of dt of the volume equals d of dt of the equation right here. And let's differentiate this. So I'll get dv over dt equals, and I'm going to have to use the product rule here, where r squared is my f and h is my g. So my f prime is going to be 2r dr dt, and g prime is going to be h is 1 times dh dt, or just dh dt. So let's plug that in. It's going to be pi over 3 times, let's see, f prime, so 2 f prime times g, so 2r h dr dt, 2r h dr dt, plus regular f times g prime, so r squared times dh dt, r squared dh dt. And there, I differentiated both sides, so I've compared those rates. Cool. But why does this matter? What are we going to do with this kind of stuff? What we can do with this is compare the rates of change. So if I wanted to see how the rate of change of the volume is compared to how the height of that water and the radius of that water is changing, I can do it with this function. I can also use this to find certain rates given other information. And that's the main reason we're going to use it for the problems today. So let's take an example from the book. So the variables x and y are both differentiable functions of t is time, related by the equation y equals x squared plus 3. If I want to find the dy dt when x equals 1, given that dx dt equals 2 when x equals 1. So let's take that equation, y equals x squared plus 3. I'm going to differentiate that with implicit differentiation with respect to t, though. So derivative of y with respect to t, if I want to do this notation, d of dt of the whole thing, just like we did in the last problem. So the differentiating y is going to be 1 times dy dt, or just dy dt, equals 2x dx dt plus 3, and differentiated constant is just 0, so that goes away. Cool, I got my function. Now I want to substitute things in. I want to solve for dy dt, and my x is going to be 1, and dx dt is going to be 2. So what we'll get is 2 times 1 times 2, which will be 4. So dy dt equals 4. Cool. Let's figure out another way to organize what I just did there, because those problems aren't always going to be as straightforward. You want to write down a few things. You want to write down your equation, your given rates, and what you want to find. So your equation is, sometimes it's the equation you're given for the problem, or if it represents some sort of real life situation and we have a shape, you have to write the equation of that shape, like the volume of that conic section. Sometimes you also should draw a picture if you can. You want to write down your given information. It's usually given rates. So which rates are you given in the problem? So write that information down. And then you want to write down what you want to find. So it's usually a rate you're trying to find. So if I want to do that last example, the equation I'd write down is y equals x plus 3. The given rate, so I was given dx dt when x equals 1. And I wanted to find dy dt when x equals 1. So if you write that information down, it'll be a lot easier to process problems. Let's take an example from the book, Ripples in a Pond. So a pebble is dropped in a calm pond, and it causes ripples that form concentric circles. So like circles going out like this. You've seen this before if you've dropped something in a pond. And when you're doing circles, as shown, so the radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So first thing you got to do is we got to write our equation. So what equation is going on here? I wasn't given one, but I was told this is forming circles, concentric circles. And if circle, this is our radius, and what is the area of a circle? Area of a circle is equal to pi r squared. So there's my equation. Now, what is my given rate? So I'm given some information. What rate? This is the second sentence. The radius r of the outer ripple is increasing at a constant rate. So there's your radius r is increasing at 1 foot per second. So there's your hint. R is the variable, so it's dr dt is increasing at 1 foot per second. We're going to say 1. Now, what are you trying to find? What I'm trying to find is when the radius is 4 feet, at what rate is the total area of disturbed water changing? The area changing, so that's dA dt, when r equals 4. So I want to say find dA dt when r equals 4. All right, there's my given information. Let's start figuring this out. If this is my equation, I have to differentiate this. So it's going to be d of dt of the whole thing of a equals pi r squared. So differentiate a is going to be dA dt is going to equal pi or 2 pi times r dr dt. So r squared is 2r dr dt. Okay, cool. Now I want to just plug things in. So for r, I'm going to plug in 4. So I get 2 pi times 4. And dr dt, I plug in 1. So then your dA dt is going to be 2 times 4 is 8 pi. And don't forget units. This is area and feet per second. So it'll be feet squared per second. And that's your answer. That's it. So you write out this information. It'll be much easier to solve. Let's try another one. So you're inflating a balloon this time. And the air is being pumped in a spherical balloon at a rate of 4.5 cubic feet per minute. And that's your rate. Find the rate of change of the radius when the radius is 2 feet. So I've drawn the picture for you right now. You're pumping up the balloon. Now, your first thing is your equation. You're not given an equation, but we're told that we're pumping up a spherical balloon. The volume of the sphere is volume equals 4/3 pi r cubed. This is in either the front or the back of the book if you're looking for that. And what you want to find, you want to figure out what you're given. Well, it's right here. You're given air is being pumped into the balloon at a rate of 4.5 cubic feet per minute. Another way to say that is the volume is increasing of the balloon because the air increases the volume. So that means what's changing is the volume, so dV dt at 4.5. So 4.5, which is, I'm going to write it as improper fraction, 9/2. Either way. And then what are you trying to find in this case? We're trying to find the rate of change of the radius. So the radius is going to be r, so dr dt, when r equals 2 feet. Cool. So let's differentiate and plug things in. So dv of dt is going to be 4/3 pi, so 4/3 pi times r, it's going to be 3 r squared dr dt. And the 3's are going to end up canceling out. So then you're left with 4 pi r squared dr dt. Okay. At this point, I can plug things in. Well, I'm trying to find dr dt, so let's rearrange this equation. I'm going to divide by 4 pi r squared on both sides. So what you'll get is dv dr dt equals dv dt all over 4 pi r squared. And at this point, you're going to plug in 9/2 or 4.5. We can just plug in the decimal. 4.5 in for dV dt times 4 pi 2 squared on the bottom. And this is something you should plug into a calculator. And if you do that, you're going to get 0.09 feet per second. And that is the rate of change of the radius. All right. That's it for examples. We'll do more stuff in class, and see ya.